Okay, hi guys. Let's get started. Okay, so we are learning how to build a data path in a single cycle process architecture, right? So, so what are data paths? What are data path elements? So you can think a data path element is a hardware component that process certain data or the addresses. So in a single cycle process architecture, so we can say that database elements are instruction memories, and then register file, so ALU, and the data memory, and then some other hardware components such as multiplexers. So in the previous class, we learned how to build these data path elements. Okay, so and then also we learned that in the previous class. So we learned that to execute an instruction, so we require 5 steps. So what are 5 steps? Instruction fetch, instruction decoding, execution, memory, and write back. So we can design a single cycle process architecture hardware based on these required steps. Okay, so we are learning how to build these single cycle process architecture step by step. Okay, so we learned about how to design instruction fetch step, right? So instruction fetch step includes program counter register and then the instruction memory. Then this is program counter. Then we learned how to design these elements, right? Okay, so and then in the previous class, we learned how to design the immediate generator. Okay, so so we learned that the load instructions and then some arithmetic immediate instructions like add I. Uh, these instructions have I-type instruction format. Okay, and then this I-type instruction format includes the immediate data. Okay, so what is an immediate data? So immediate data is the 12-bit. So 12-bit two's complement constant data, right? So actually, so then where is okay? So this is the some data path. So which means that the data flows from the immediate data, and then from these 12-bit immediate field, we can generate the immediate number, right? But so, so actually we can use these immediate data for the arithmetic immediate instructions such as add I, right? And then also we can use these immediate data for load instructions or store instructions. Okay, for the load word or store word instructions, so we can use immediate data for generating addresses, right? So which means that we need to use the ALU. So with the ALU, we can perform various types of instructions, various operations like add operations, sub operations, or multiply operations, something like that. So actually, so immediate instructions, so arithmetic immediate or the logical instructions require the same type of operations. Okay, and then think about the load word and store word. So these memory type instructions require add operation. So we can use this immediate data to as the input of ALU, right? So then the ALU received the 232 input data, right? So immediate number needs to be extended into the 32-bit data. Okay, so as you can see, so we learned how to extend the immediate data in the included in the instructions. Okay, so in the I-type instructions, the immediate data is included in the first 12-bit field, right? And then, as I mentioned, this immediate data needs to be extended into the 32-bit data. So, and then, you know, this immediate data is the two's complement data, right? So, what is required? What is required for this sign, the bit extension? So we need to apply sign extension. Okay. We need to apply the sign extension. Okay. So as you can see, the sign bit is repeated. Okay. So we can apply this so sign extension for this I type data, and then S type data, and then B type data, and that includes the immediate numbers, right? So based on the instruction encoding rule, okay, so we can generate the 32-bit immediate data, right? Okay, and then let's learn about the behavioral model of data memory. So actually, in the previous class, we learned how to design instruction memory. Okay, so as we learned, what is the memory? What is a memory device? A memory device is a data array. And then this data array is indexed by an address, right? So data memory is the same. So, we can store data in the data memory, and then we can read these stored data in the data memory. But we can access these data using address, right? So it's the same. It's a data array indexed by an address. But if you see the data memory receive the address, and then data memory has the data output. It's a D out. So this is same to the instruction memory, but the data memory also includes the data in. Why? So we can write, we can update data in this data memory. Okay, so data memory has the D in data, and then this D in data is written to the target data space, the target data element, if the store instruction is executed. And then, so for this control, the data memory has the mem read port. So this is the control port. So if the mem read port is 1, then the read operation is activated. Then the data memory has the mem write port. So data write is activated if the mem write is 1. So how can we implement this data memory? So in the data memory implementation, we need to implement the write operation and then read operation. So what is the read operation? So like the instruction memory, though we can read data indexed by an address. But also in the data memory, the data array in the data memory, so you can observe that also the data array is declared. Then what is the size of a single data element? The size is 32-bit, right? So as you can see, this size is the 32-bit. So actually, so the CPU or the most CPU or most processor uses the byte address. Okay, so it means that the 1 byte data is mapped to the address 1. But so in this example, so I just used the 32-bit data element in a data memory. So it is because so in this course, so actually, so we are implementing a processor that only supports the load word and store word instructions. Okay, so what is the word? Word is the 4 byte of data. Okay, so that's why I just define a size of a single data element is 32-bit. Okay, so because so this processor, so this processor just supports the load word and the store word instructions. Okay, and then so in this example, the data memory also includes the 256 elements. Okay, so what is the read operation? The read operation. So this data is indexed by an address, but the size of a single data element is 4 byte. So how can we index the target data? Okay, so so like the instruction memory, right? So we can just like this is the data and the index is address divided by 4. But I mentioned that so actually we can remove remove the LSB 2 bits for this divided by 4 operation, right? So and then this operation is only activated if the mem read control signal is 1. Okay, so otherwise the output is 0. And then also you can find the write operation. The write operation is synchronized by clock signal, like the register file and some register like the register file operation, right? The write operation of register file. So it is because so we need to avoid the the combinational loop for this write operation. Okay, and then the detailed of this write operation is explained in the lab document. Okay, so I mentioned that the write operation is need to be synchronized with the clock signal, right? Then so on the rising edge of a clock, so it's a positive edge, and then if the mem write is 1, then write operation is activated. So how can you define the write operation? So so this is the inverse of the read operation, right? So the output data, the out equal data. Oh, no, no, no. The target of write operation is the data array, the one of element in data array, right? So data, and then what is the address? Also, the address is divided by 4 because we just support the store word instruction, right? So this is updated by data in. So this is the write operation, the write operation of the data memory. Okay, and then how about the branch instruction, like the BQ? So if you see the branch instruction like BEQ, x1, okay, I just used rs1, rs2, and target. Target is the immediate data. Okay, so branch instructions require two source registers. And then, so what is required? We need to check the equality of rs1 and then rs2. So how can we check the equality of two data? So we can check like the rs1 minus rs2, right? And then we can check the output is 0. So what is required? For this operation, the subtraction is required. And then we can just perform this subtraction operation using ALU. Okay. And then, so we can check. So if the subtraction of two source registers is 0, then which means that the condition is true. If the condition is true, then PC is updated by current PC, the PC of the branch instruction, and then plus immediate number. Okay, so we learned how to generate the immediate number. Okay, let's see how the branch is performed. So as I mentioned, the branch instruction requires the two source registers, and then you can get these uh, the values of two source registers from the register file. Okay, and then these data, the register operands, are given to the ALU, right? And then the sub operation will be performed, and then so like the rs1 minus rs2. So this operation will be performed, and then the result will be generated. But branch instruction will not use this result. Branch instruction needs to check this result value. And if this result value is 0, then the condition is true, right? So in order to support this operation, we can add the 0 output. So 0 output becomes 1 when the result is 0. The result of ALU is 0, then this 0 output, the output of ALU becomes 1. Okay, and then also, so we can generate this immediate number. Okay, immediate number from this branch instruction. So actually, so if you see this how the immediate data is generated by this branch instruction. Okay, so as I mentioned, the B type instruction, this is the branch instruction. The B type instruction does not include the LSB of the immediate number. So it is because the immediate number of branch instruction is always multiple of 2, right? These even numbers, right? So uh, the immediate number of the branch instruction just includes this uh, bin number 1, okay, until the bin number 1, okay. So as you can see, the instruction 11 down to 8 is included here, and then we need to add the missing this 0, okay. So and then we can just generate this 32-bit immediate number of the branch instruction, okay. So actually this synapse 1 uh, represent this addition of the 0 bit, okay, the number 0, the pin number 0, okay. So then we can just perform the PC plus immediate, and then this immediate number is the 32-bit immediate number. So here, so we can calculate the target of the branch instruction, okay. So these are the database elements, so like register, ALU, and then this adder, the adder for the PC plus immediate number operation, right? So these are the hardware components required for branch instruction, okay? So, and then, so this is important. So in a single cycle process architecture, then we need to complete the the required steps of instructions within one clock, right? And then within one clock, so which means that within one clock period, like this is the period, then we can just use this one data path element. So which means we can just use the one data path element, so one hardware component for only one function, okay? One function at a time. So which means within this one clock period, so if we just use the one data path element, then this data path element needs to be used for only one function, okay? So that's why we need to separate the instruction and data memories. So actually when we learned about this stored program model in a processor, then I mentioned that actually the instruction and data can be stored in the unified memory. So we cannot distinguish it. We cannot uh, we do not separate the memory space of the instructions, or we do not separate the memory space for this data. So we can the instructions and then data are stored in the memory space, and then we can just access this instruction or the real data using the memory address. But so in a single cycle processor design, then you can observe that we use the instruction memory. So here is the okay. So instruction memory and data memory. So memories is separated. Memories are separated. So it is because of this one. Within one clock period, each data path element can perform only one function. Okay, and then for the memory, accessing the memory is the one function, but we need to access this memory for fetching instructions using the program counter. So this is the address of the instruction. Also, we need to use the data memory for load word or store word instructions. Okay, so we need to separate the instruction and data memories. Okay, so this is the reason. This is the reason why we need to separate the instruction and data memories. And then if a certain database element requires some alternative data sources, then we can use the multiplexers. Okay, so let's see the example. So this is the example. Okay, for all time and then load or store instruction. So these are memory instructions. So in order to execute these all time and memory instructions, we need to use the register file, right? And then ALU, and data memory. But so let's see that this multiplexer. So you can find that the ALU receives the two input data, right? So in 0 and in 1. But for the second input port, so you can observe the multiplexer. So this is because the ALU needs to support the two different types of instructions, like R type instruction, like add RD, RS1, RS2, right? Also, the ALU needs to support the I type instruction, like add I, the, like the RD, RS1, and immediate. But so required operation, the requested operation is the same. The request operation is the same add operation, right? But this ALU, for the second input of the ALU may require the RS2 or immediate data, right? So based on the type of instruction, the the second input port of ALU can use the RS2 or immediate data. So I mentioned or. So in this case, so we can use the multiplexer. So what is the multiplexer? So based on the selection signal, the multiplexer, the output of a multiplexer can be connected to the one of two inputs, right? So this is so as you can see, this is the output of register file. So one of input is connected to the output of a register file, and then one of input of this multiplexer is connected to the output of immediate generator. And then we need to select these two inputs connected to the second input of ALU. So, and then we need to define this selection signal, ALU source. Okay. Also, you can find another ALU here. What is the purpose of this ALU? So let's see that. So this ALU is used for selecting input input for destination register. So what does that mean? So if you see the add instruction, like add RD, RS1, RS2, and then also you can find the load word RD, RS1, and immediate. So you can find the two RD here, but this RD is the output of ALU. And then what is this RD? This RD is the output of memory, right? So the RD is the same. The RD is the the right data. This all is the right data of the, okay, this is connected to the right data port of the register file. But based on the instruction, like the alt type instruction and then load order instruction, the RD uh, can be from the ALU out, like here, ALU result, and then the RD can be from the output of memory. So we need to select, okay? I said or, okay? So the RD can be the result of ALU or the result of data memory. So in this case, we need to use the multiplexer. And then this multiplexer will be selected by mem2ref selection signal, right? So in this case, we need to use the multiplexer, okay? So this figure shows the full data path of the single cycle processor architecture. So in the previous class and then the current class, I explained the data path, the design of data path element for the 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 operation step of instructions, or so some the record steps for different type of instructions. So we can just merge these database elements in a one place. Then we can just build the hardware architecture of single cycle processor. So as you can see, the database element such as the PC register, instruction memory, the register file, ALU, and the data memory. So these database elements are connected. So input and output ports are connected. Okay, you can just follow the data flows the from the, the output of the database element to the input of database element, right? So you can just connect the data flows, the data from the data port, the data in out port of this data path element. Okay, so we can also add the multiplexers. So if some alternative uh, inputs are need to be selected by different type of instructions, right? And then you can find some port. Okay, so you can find the multiplexer here. So data path element can have control inputs. So what is the control input? So control signal just determines the operation mode of a data path element. So for example, you can find the mem read port here. So as I mentioned, the read operation, the read operation of data memory is activated if the mem read is 1. Okay. Also, the write operation is activated if the mem write is 1. So you can find the ALU operation here. So ALU operation determines the target function of ALU. So you can find the selection signals here. So these signals are called control signals. So firstly, we define the required operations. Required operation for some steps, and then the required operations of instructions. And then based on these required operations, we can just design data path element. Okay, so which means we can define the function of data path element based on the required operations. Okay, and then we can just connect the input and output ports of data path element. like this. So then we can build the entire full data path of the single cycle processor. But we can observe some control port, control signals. So which means we also need to design control unit, the control unit of this single cycle processor. Okay. Okay. So as I mentioned, we require the control unit. The control unit just defines the values of control signals. So you can find that the control unit generate the control signals like the regular write and then ALU operation, the membrane and membrane. Okay, and then we can generate these control signals based on the instruction, right? Okay, so this the control unit needs to generate the control signals based on the instruction types. Okay, so firstly, let's see how to define the ALU control signal. So what is the ALU control signal? So you can find the ALU operation here. So what is the ALU? ALU just performs the defined function, and then the ALU receives the two input data and then generate the output. So this is the output of ALU. Then the function, this type of function is determined by ALU operation control signal. So you can find the ALU operation control signal here. So let's see how we can define this ALU operation control signal. So firstly, we need to define which operations are required by instruction types. So which operations are required? So both load and store instructions, the ALU needs to perform addition. So this is because the ALU needs to perform RS1 plus immediate, right? And then for the branch instruction, the ALU needs to support the subtraction. Why? We need to perform RS1 minus RS2. Okay, then we need to check if the result is 0 or not. And then for all type instructions, the ALU needs to perform the defined instructions. Okay, and then we assume that this this single cycle processor just supports the add operation, add instruction, sub instruction, and end instruction, and or instructions, right? So we this process just support the four arithmetic and logic instructions, right? So we can just define the function of ALU like this and so if the ALU just supports the AND operation, so we can just define the ALU operation is 0, 0, 0, 0. And then for OR, so this is the 0, 0, 0, 1. So alt type instruction, we can define some required functions by ALU based on some instructions. Okay, alt type instructions. So actually, the RISC-V needs to support some various types of arithmetic and logic instructions. So that's why the ALU control bit is a 4-bit signal. But so in this example, though we just assume that a single cycle processor just supports the AND or and add and sub instructions, right? So even though the ALU control bit is 4-bit signals, we just define these functions. Okay. So based on some OP code and then some uh, OP code and then some function 3 or function 7 field, we can define the ALU control signal. Okay. So firstly, this load word is the load instruction, and then store word is the store instruction. And then if we check the opcode field first, then we can figure out the input instruction is the load instruction or store instruction, right? So if the opcode field is the 00000011, then this means the instruction is load instruction. Okay, and then if the opcode field is the 01000011, then the instruction is store instruction. So in this case, we can just define ALOP bit. Okay, so ALOP bit is the 2-bit signal, and then this ALU 2-bit ALOP bit just classify the types of instruction, like the memory instruction and branch instruction and are the R-type instructions. So you can find that if the ALOP is 00, then which means is the memory instructions. Okay, and then ALU is used for generating addresses, right? And then if the ALOP is 01, then that means this is the branch instruction. Then in this case, the ALU is supposed to subtraction. Okay. Then so you can find the ALU control bit here. Otherwise, if the instruction type is R-type instruction, then opcode field is the 0110011. So in this case, so if we just check the opcode field of an instruction, and then if the opcode field is 0110011, then we can figure out, oh, this instruction is the R-type instruction. So in this case, we can just set the ALOP is 10. So firstly, we can classify the instructions, okay, like the memory instructions, branch instructions, and R-type instruction. For the memory instruction, the ALU just needs to perform add operation, and then for the branch instruction, ALU needs to perform sub instruction, right? Then you can find that the ALU needs to perform the various types of operations for the R-type instructions. Okay. Okay, so AL, if the AL control is 0010, then you can find that this is the add operation. And then if the AL control bit is 0110 and then 0110, then this is the sub operation. Okay. Okay. So we can just define this ALU control signals firstly based on the type of instruction, the class of instruction, and then if the class of instruction is the R-type instruction, then we can need to check the other fields such as the function 3 or function 7 field. Okay. So this is, you can find the summary of the instruction. Okay. So as I mentioned, you can just check the opcode field for the load and store instruction. Okay, these are memory instructions. Okay, so and then also you can find that for the branch instruction, the opcode field is here. And then for the R-type instruction, so actually for the R-type instruction, the opcode field is different. But you can find that for the R-type arithmetic or R-type logical instructions, the opcode field is the same. Then for the I-type, I type is different, but also you can find that for these arithmetic or the logical instructions, so we can just use the same OP code field. Okay. So based on this rule, then we can define the the function of ALU. Okay. So this is this this slide shows how 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 to generate the ALU operation bit. Okay. So if the ALU OP is OP bit, okay, so this is a 2-bit signal. If this bit is the 00, which means the instruction is memory instruction. So in this case, we need to generate the 0010. But if the ALOP is 00, we don't need to check the function 7 or function 3 field, right? And then if the ALOP is 01, so which means the LSB is 1, we don't need to check the function 7 or function 3 field because we always need the ALU always need to perform sub operations. Okay, and then for the R type, if the ALOP 1, pin number 1 is 1, then this means this is the R type instruction. Then we need to check the function 7 and the function 3 field. Okay, so the control unit, we can just add the control unit like this. Okay, so what can you observe? So instruction, the instruction for the 32-bit instruction field. Okay, so in the instruction memory, so we can read the instruction, right? And then the instruction is the 32-bit data, and then we can check the instruction bit pin number 6 down to 0. Then this is the OP code, OP code field of the instruction. Then this OP code field is given to the control unit. Then control unit can generate these control signals. So so you can find that the branch branch means if the OP code field is the branch instruction, then branch will be 1. So you can find the other control instruction, control signals such as the mem read, mem to read, then ALOP. So ALOP is the 2-bit signal. Okay. Then mem write, AL source, and then reg write. And then so ALOP, 2-bit ALOP signal is given to the ALU control unit, right? And then by checking the function 7 field and then function 3 field, we can finally define the ALU operation signal, ALU control signal. Okay, so 4-bit ALU control signal. Also, you can find that the control signals are connected to the control signal port, and then the selection port of the multiplexers. Okay, so this is the final hardware design of the single cycle processor. So then let's see this how the R-type instruction is working. So PC is updated, and then using the piece, then we can access the instruction memory, then we can get the instruction, the 32-bit instruction, right? So you can find that this instruction is the 32-bit. And then if the instruction, we can just check the instruction opcode field, right? And then the R-type instruction, then this is the RS1, okay? RS1 field. This is the RS2 field. This is the RD field, right? So, and then we can get two register operands based on the RS1 number and RS2 number, right? But you can find that there is a multiplexer here. Then which signal needs to be selected by this multiplexer? To the R type instruction, then we need to activate this, the second, the register operand, right? So RS2 data. So the selection signal of this multiplexer needs to be 0, right? So we can define control a control signal like this. So this is the R type instruction, right? The R type instruction, and then for the R type instruction, then this multiplexer needs to select the output from register file, the RS2 data. So the control signal needs to be 0, right? And so the branch is 0 because this is the R type instruction. Now how about the mem read? Mem read also needs to be 0 because we don't need to read memory, and the mem write is also 0. So we don't need to write data memory, right? Now how about the mem to reg? So for the R type instruction, the RD, the data for register update comes from ALU. So for this multiplexer, we need to select this input, right? So in order to select this input, then this mem to reg needs to be, so you can find this 0 here. It is 0 also, right? And then how about the regulate? Regulate needs to be 1 because R type instruction needs to update the register file, right? And the ALOP is 1, 0 by definition. Okay, so you can find some definition here. So we can define the output of a control unit, output of control unit like this, the R type instruction, right? It's not difficult, right? So load instruction, okay? So you can also check this instruction. So the branch is 0, and then load instruction. For the load instruction, we need to read data memory. So mem read is 1. And then ALOP, this is the memory instruction. So by definition, these bits need to be 0, 0. Up the mem right, it's 0 because this is load instruction, and then it requires memory read of the ALU source. So ALU needs to perform add operation, but the we need to perform the ALU needs to perform RS1 plus immediate. Okay, so the one of input of this ALU, the second port of this ALU needs to be the immediate data. So in this multiplexer, we need to select the port 1, right? So ALU source needs to be 1. How about the regulate? The load instruction read data from the data memory and update the destination register using the read data, the data read from the data memory. So regulate needs to be 1. the mem to reg also needs to be 1 because it up it the written data, the update data to the register file comes from memory. Okay? So we can define the control signals like this. Okay? So you can also generate the control signals for the branch instructions. Okay? So branch instructions, obviously, this is 1, right? Branch is 1. So if the branch is 1, then one of what is this one? This one is AND gate, right? And then one of the input of this AND gate is branch. And then for the branch instruction, okay, we can check the OP code field of this instruction. Then if the instruction is the branch, then it becomes the 1. Then the output of this AND gate is determined by this signal. So what is this signal? It's 0. So what does that mean? Branch instruction, like BQ instruction, performs the RS1 minus RS2, right? So for this mux, the AL source needs to be 0 because we just used the RS1 and RS2. And 0 means that if this is the result of ALU, and then if the result is 0, then this 0 becomes 1. So what does it mean? What does that mean? It means the BQ is true. The condition of BQ is true. If the condition of the BQ is true, then it becomes 1. And then what is the output of AND gate? This AND gate, it's 1. And then what does that mean? So you can find that this is the PC plus 4. And then this is the PC plus immediate, right? So this is the immediate of branch instruction. And then this is the PC. So if this output of AND gate is 1, then this one is selected, and then this one is given to the program counter. So we can jump to the target of a branch instruction. But if this AND gate the output of AND gate is 0, then PC plus 4 is selected. Okay, this is the control signal control of branch instruction. Okay, we complete the single cycle processor. And then, this single cycle processor can execute the RISC-V instructions within 1 clock cycle. But this single cycle processor has performance issues. Okay? Is it because, execution time is the instruction count multiplied by CPI and multiplied by TC. And then for the single cycle processor, what is the CPI? The clock per instruction. This is 1. Okay, and then instruction count is determined by software and compiler, right? So actually, the performance is determined by clock period. But we learned that the clock period of the system needs to be greater than the delay of critical path. So, okay, so let's see the load instruction. So how can we calculate the delay? So these are data path element, right? And then data path elements have delays. Okay, each data path element has delay, right? So actually, the PC has the delta T PC, and then instruction memory has the delta T instruction memory. Then register file has the delta T the delay. And then also ALU has the delta T. Then data memory has the delta T, the delay of the data memory. And then, so in order to execute this load order instruction, then we need to use the program counter, instruction memory, register file, ALU, and data memory. Also multiplexers. So we need to accumulate. We need to accumulate the delays of these components. We can just accumulate. We can just accumulate the delays of these data path elements. Okay, so this is the critical path of this single cycle processor. The critical path is the load instruction, because the load instruction demands the all data path elements, right? So like the PC instruction memory, register file, ALU, data memory, and register file write. Okay, so this is the longest delay. The longest delay of in a single cycle processor is the delay of load instruction, and the delay of load instruction determines the clock period. So TC clock period needs to be greater than the, the, the accumulation of all delays. Okay, so and then the problem is that for the single cycle processor, the TC, the clock period is large. And then it means the performance is low. And then, so so in a digital design, we need to use the same clock signal, right? So which means the clock frequency is fixed. We don't need to. So usually we cannot use the variable clock frequencies, okay, for the different instructions. Okay, so this is the performance issue of the single cycle processor. The performance. What is the performance issue? The clock period. The clock period is long because the delay, the the delay of the critical path is also is large. Okay, because we need to accumulate the delays of all data path elements. Okay, so now in the next class we'll learn about the pipelining. So in order to improve the performance, we can use the pipelining concept. Okay, then we will learn about this pipelining concept in the next class. Okay, so this is actually very important. Okay, so I will stop here. Then please watch this video and then see you in the next class. Thank you for attention.